All right, we're gonna get started here with these quick questions and everything. So, next time you meet, you gotta have a text, huh? So I emailed out the link. It's kind of like, there's only 30 questions on that test, but I kind of got it outlined there, right, for you. So we will finish up today now on the test at the bond triangle, which we'll cover today, and then some signified lines. So we should be in perfect shape. Hopefully you poked around quite a bit in OWL and started that. Especially the chapter, the last OWL assignment, right? The last OWL assignment gets to be pretty long. So, and after today, you'll have this back on. So, all right, well, let's get right into it here then, so we can finish everything up. So I've got 13 circled around here that's on the board. So this would be I3. So how many valence electrons is going to be 3 times 7 plus 1 because of the charge, right? And group 17, so we got 3 times 7 plus 1 for the negative charge. We're looking at 22 valence electrons. And let me zoom in. So we're going to do I. Now, no bonds for anything, no double bonds for anything in group 17. Iodine, bromine, chlorine, stuff like that. So we're going to do our terminal atoms. That gives us 16. We've got 6 left. Those 6 are going to have to go around the central atom. This charge, so typically you'd see it look like that. And then you can do your, what do we got on this? We got a 2, 3 on this, right? Or bonding domains and non-bonding domains. Well, it looks like a 2, 3 out of that. 13, 14. So both of these are in group 17. We're both in group 17. There's 6 of them. So 6 times 7 is 42 electrons. So this is kind of nice. These are in group 17. You know there's no double bond. You can just throw this thing down in a hurry. You got to connect them. So far, that's 10 electrons, right? So we got to connect them. We got to complete the octets out here. So far, that gives us 40 electrons, right? So we're just going to slam 2 into the middle, into the central atom. So our 42, we can put them anywhere, it doesn't matter. So that gives us 5 bonding domains, 1 non-bonding domain. Now, notice the word approximate on 15. So if you have Ni3, this will be 5 valence electrons. 3 times 7, 21. You got 26 valence electrons, huh? So with 26 valence electrons, and the iodines. That gives us 24. So we got to put 2 there now. So our bond angles are going to be for a 3-1, but notice the word approximate. So whatever we get for bond angles for a 3-1, approximately, closest one for a 3-1. All right, exceptions to the octet rule. In 17, less than 8. This right here is on here. Hopefully you've seen this so many times, but you have to actually draw all these out. So less than 8, I can guarantee you, is boron. So if you actually drew this out, boron is going to be the central atom, and it only has 6 electrons. Now, typically something greater than 8, and you can see, I don't have it on here, do I have it? Yeah, it's right here. XEF4 is actually on here. So if I look at this picture, I've got 2, 4, 6, 8, 10, 12 electrons in the central atom for XEF4. So we know this one right here is greater than 8. And let's see, we could draw out this one. I don't know. Let's see, we got F, F, F. So for the valence electrons for this, both of them are in group 17, so we're looking at 28. 28 valence electrons. Oh, that's a chlorine. Cl. So this would give us, again, the nice thing is we know we don't have to worry about double bonds, resonance structures, or anything like that. So if we draw this gives us 24, 5, 26, 27, 28. So the central atom here, how many electrons are on the central atom here? But we've got 10. So it looks like that one works. $19 is this. In order to get a hydride is hydrogen with a -1 charge. So if we're going to put something in front of the hydrogen, I'll just go like this. XH, hydrogen gets the -1 charge. If hydrogen gets the -1 charge, it has to be the higher electronegativity. And the electronegativity is on the back side of our periodic table, and hydrogen is 2.2. So the electronegativity of hydrogen is 2.20. The bond dipole, maybe at lab or talking about it, we know that the negative charge has to point towards hydrogen. That means the electronegativity of this element here has to be less than hydrogen. For hydrogen to win. So you're just looking at the electronegativity here of this atom here has to be less than 2.20. Otherwise, if it's more than 2.0, it's going to get assigned the negative charge, and hydrogen will get assigned the positive charge. So you're just looking for something here that is less than 2.20. 20 and 27. 1, 2. Greatest ionic character is going to be the greatest electronegativity difference. For this, you're looking for the greatest electronegativity difference. It's going to be the greatest ionic bond character. And then 27. Which of the following is non-polar? Now, for it to be non-polar, there's two things that have to happen. Number one, outside, this is, of course, there's an exception. Outside terminal atoms should be the same. So the pull is equal, right? The outside terminal. Number two, those are such so everything cancels. All of these compounds are tetrahedral. Stay right here. And I'll show this one because I think this one comes up in the lab. And you see Cl2F2. And you say, well, I'm going to draw it like this, and I'm going to put the chlorine here, and I'm going to put the chlorine here. So up versus down is going to cancel. And I'm going to put the fluorine over here. So right versus left is going to cancel. That is not the case. That is a two-dimensional drawing representing this three-dimensional structure. There is no way to put two of these across from each other and get them to cancel. So the only one that has the terminal atoms the same is that one, right? That's what's going to cancel out. The rest of these cannot cancel out. The terminal atoms are not the same. Okay, so we will finish up. Oh, I think I just lost this. Yep. So we'll finish up, and probably at the end, we'll have enough time to come back and look at these quiz questions. So let's see, we are at, we're around page 10, which is the bond triangle. Can you hear me back there? Yes? All right. So let's see where we're at here. So last time we looked at these bonds and we said if the electronegativity difference is less than 0.39, we have nonpolar covalent. If it's between 0.4 and 1.79, it's polar covalent, and greater than 1.8 is ionic. When you have another textbook, those numbers could be different. So that is not set in stone. Well, a more accurate representation of what you have for bonds is this bond triangle. So find this bond triangle. So on this bond triangle, this region here is ionic. This region here is covalent. This region here is metallic. And this region here is semi-metallic. Now, for a metallic bond, that's the only thing we haven't talked about yet. I don't think we talked about it. Now, I put it this way. The nearest power, let's do a power plant. We're getting electricity from these lights, let's say some from the nuclear power plant at Red Wing, Minnesota. Quite a ways away, right? So, I put it to you this way. I roll a water hose out from here to Red Wing, Minnesota, and it's full of water. And I want water to come right here, right now. If they turn the water on in Red Wing, Minnesota, boom, do I get water out here? I do, if the hose is full of water, correct? Now, a metallic bond is due to the electrons around the atoms. What is electricity? It's the flow of electrons, just like water is flow of water, if you will. So if they hit the power switch in Red Wing, Minnesota, does the electron instantly come from the power plant? Boom, here? No. It pushes electrons into the wire in Red Wing, Minnesota. We get electrons out. It's not an instant. Just like the water, you're adding water to the hose in Red Wing, Minnesota, we're getting water out. So a metallic bond is just these electrons around the metals called delocalized electrons. So if you have something like copper down here, and we've got copper like this, and I guess I can put it like this. You've got the electrons around the copper. Electrons around copper. These are called delocalized electrons. These delocalized electrons, they really don't care what copper they're around. So a metallic bond is just what's called these delocalized electrons, because I can bend this, I can flatten this, I can push electrons in to the end of the copper wire. This electron could go to this copper, and this electron could go to this copper, and guess what? I've got a flow of electrons, just like I have a flow of water. So a metallic bond is just these delocalized electrons. Now, what do we get for a covalent bond? This is the electronegativity difference. So there's the electronegativity difference on the y-axis. Previously, that's all we talked about. Oh, you get a covalent bond if the electronegativity difference is between 0.4 and 1.7. Well, this is not very accurate. So what we do is we add the x-axis, which is the average. Now, let's look at the pattern here. The most covalent bond is in this corner. How do you get then most covalent character? Want the electronegativity difference to be low, correct? You want the electronegativity difference to be low. But you want the electronegativity average, look at where the average is the highest, in this corner, correct? You want high electronegativities close. Where are we going to get high electronegativities? In this top right corner. Where do you get an ionic bond? Way up here, when you have the greatest electronegativity
difference, right? The greatest difference. What's the highest electronegativity out of all of them? Fluorine. So what do you think the lowest is? Probably cesium. So you're going to have high numbers here combined with low numbers down here. Where do you get metallic bonds? You want a low difference on the y-axis and you want a low average, right? If you have a low average, you're talking metals over here. So let's do an example. I'm just going to pick out MgBr2. Let's figure out where it is on our bond triangle. Now, this is in a little different scale than what's on our periodic table. The electronegativity on this scale is Pauling's. The electronegativity with this bond triangle is on the next page. Different. It's just called Allen electronegativities. They're a little bit different. Okay. So it doesn't matter. We have an electronegativity table. Let's find magnesium on there. So magnesium on our table is right here. So the electronegativity 1.293. So 1.293 and bromine. $2.685. So my electronegativity difference. It doesn't matter that there's two of them. It doesn't matter that there's two of them. You're just going to subtract. Let's just go large minus small. So my electronegativity difference 1.392. That's on my y-axis. What is my average? Doesn't matter that there's two bromines. There's two of them bonded together. Add the two electronegativities up, divide by 2. And that gets me 1.99. That is on the x-axis. So 1.4 on the y-axis. I'm going to go up to 1.4 on the y-axis. And maybe this one's on here. 1.4 on the y-axis. So I go across at 1.4. I'm going to go up at 1.99 or 2. Oh, it's on here. There it is, right? So then we know it is in this ionic region. This is ionic. I gridded it out. I found it. It's ionic. So again, this adds another value to it. It's just not the electronegativity difference, because that's not very accurate. If you end up on this line, that's about 50-50 ionic and covalent. So if you end up on the line, you're about 50-50. If you end up on this blue region here. And likewise over here, if you're on this blue line, you'd be about 50-50 ionic metallic. Okay. So I think you'll be able to do look at a bond triangle and do a problem on that. The average and the difference gridded out. Well, we talked about whether something is polar or non-polar, whether or not it has a net dipole moment then. Are going to chapter 9 then to finish up. 8-9 is bond properties. We do not cover anything in section 8-9. So we want to talk about these bonds, and the only thing we have not covered so far on this blue sheet is hybridization column. So that is the key to chapter 9, is this hybridization and explaining hybridization. Right? So this concept of hybridization is what we need to talk about. So we're going to understand sigma and pi bonds arise through orbital overlap. Identify the hybrid orbitals used to match the electron pair geometry of the central atom, which really is hybridization. The idea that bonds are formed by the overlap of atomic orbitals is the basis for valence bond theory. In summary, the main points of the valence bond theory of bonding are that orbitals overlap to form a bond between two atoms. Two electrons of opposite spin can be accommodated in the overlapping orbitals. Using one electron is supplied by each of the two bonded atoms. The bonding electrons have a higher probability of being found within a region of space influenced by both nucleus or nuclei. Both electrons are thus simultaneously attracted to both nuclei. What is a sigma bond? A bond formed by the overlap of orbitals head to head and with bonding electron density concentrated along the internucleus axis. When bonding occurs along the bond axis, it is referred to as a sigma bond. So here's some examples. If you just make H2, what do you have? It's pretty simple here. You have one hydrogen has one electron, one valence electron, correct? So it would make sense that if we have one electron here with upspin and one electron here with downspin, they would come together to make this bond. So this is the overlap of 1s orbitals are overlapping. We just got a sigma bond. 1s orbitals overlap. Now, if you want to make the compound hydrogen fluoride, you also have a sigma bond. How do you do it? it's the overlap of a 1s for the hydrogen, but it's a 2p for the fluorine. So you get a sigma bond again, a 1s from 1, and again, you'd have opposite spinning electrons. Well, how do you get an F2 bond? Well, it's going to be the overlap of 2p orbitals on the 2 fluorine atoms, forming a sigma bond. Well, all that's fine and dandy. Seems to make sense. You're going to have one electron spinning one way and one electron spinning the opposite way of the other. However, this becomes the problem. Using only atomic orbital overlap will not explain molecules with more than 2 atoms. For example, carbon and hydrogen combine to form CH4, even though carbon only has 2 unoccupied p orbitals to bond with. This is carbon's valence electrons, or its electron configuration notation, 1s2, 2s2, 2p2. So you would think that you're only going to get 2 bonds here with carbon. But we don't get 2 bonds, we get 4 bonds. And they get as far apart from each other as possible. So that's what we have to explain. So to solve this dynamic, Linus Pauling proposed the theory of orbital hybridization, in which new set of orbitals called hybrid orbitals could be created by mixing the s and p orbitals on an atom. There are 3 principles that govern the outcome. The number of hybrid orbitals on an atom is always equal to the number of atomic orbitals that are mixed to create the hybrid orbital set. So we're going to be mixing s, p, and d orbitals. They're not s orbitals anymore. They're not p orbitals anymore. They're hybrids. They're sp hybrids. By hybridization, for sp hybridization, which orbitals mixed? 1s and 1p. How many hybrid orbitals do I have? I got 2 equivalent orbitals, right? So this hybridization, this is how many orbitals come together. You're just adding up the superscripts. If you have, how many new orbitals do you have? And s got together with 2 of the p orbitals, so you have 3 equivalent orbitals. sp2 again, 3 equivalent orbitals. sp2, 3 equivalent orbitals. Now you have sp3. How many new orbitals do you have? And s got together with 3 p's. You have 4 new orbitals. They get as far away from each other as they can, and we end up with this shape. This is sp3, 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 so 4. When we get down to here, how many orbitals came together? This ends up being 5, right? 1d, 3 p's, and an s. 5, 5, 5, 5. This gets us our trigonal bipyramidal. That's how all 5 of these get as far apart from each other as they can. 120 in the middle, and then 90. How many orbitals came together here? 6. 6. Okay. We are going to look at that. In fact, you're going to see 2 carbons. The first video I'm going to show is 2 carbons that both are sp3 hybridized. That is this structure. Carbon-carbon single bonds. The next video is going to be two carbons that are sp2 hybridized, which is this structure, carbon-carbon double bond, two hydrogens. The third video will be two carbons that is sp hybridized, which explains triple bonds. Hybridization will also explain why we get double and triple bonds. Now, I've searched hundreds of hours, hundreds of videos to find the right ones. This video nails it. Please do not be on your phone. I'm going to show you the videos that really do a great job of hybridization. And if you want to see, they're right here in this learning guide. So hopefully this opens up perfectly. And we get to watch a commercial.
The fact that this reason showed up at this exact moment proves that
I actually think that's pretty cool.
Let's first start by examining the shapes of the atomic orbitals for carbon. The 2s atomic orbital is a sphere, and the 3 2p atomic orbitals are shaped like dumbbells, oriented along the three axes, 2px, 2py, and 2pz.
Nothing new there. S orbitals, dumbbell shaped P
Think
orbitals.
of these 4 atomic orbitals as three-dimensional shapes, where you are most likely to find an electron 90% of the time. Notice that the electrons have access to both lobes for the 2p orbitals. Starting from the abbreviated electron configuration for carbon, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pc atomic orbital. Although we now have 4 paired electrons for bonding, we still can't explain the experimentally observed bond angles for a tetravalent carbon. Thus, when
So far, pretty simple. One went out of the S into the P, correct? Pretty simple so far.
we mix the 2s atomic orbital with all 3 2p atomic orbitals, we create 4 new degenerate energy hybrid orbitals.
So it's pretty simple. 3 P's and an S come together. They're not S orbitals anymore. They're not P orbitals anymore. They're sp3 hybrid orbitals. How many do you have? 4.
The shape of the new sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes, where you can find the electron 90% of the time. The hybridized carbon now possesses 4 unpaired valence electrons and is said to be an sp3 hybridized carbon. When we superimpose all 4 sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. The 4 new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of the tetrahedron with all angles at 109.5 degrees. Your instructor will often draw the sp3 hybridized carbon on the blackboard as shown. The 2 solid lines in this drawing are in the plane of the board. The wedge represents the electron coming out of the plane of the board, and the line is the electron going back behind the plane of the board. Each of the 4 sp3 hybrid orbitals contains 1 electron capable of forming a covalent bond. The sp3 hybridized carbon is now capable of forming 4 covalent bonds. Here, X represents any atom with a valence electron capable of forming a covalent bond. Because the electron density is symmetrically located about an imaginary line that runs through the two adjacent nuclei, we call these bonds sigma bonds. Example of a simple carbon compound with an sp3 hybridized carbon is methane, CH4. The ideal bond angles are all 109.5 degrees due to all four equal in size hydrogen atoms attempting to get as far away from each other as possible. Your instructor will often draw methane on a blackboard as shown. Again, the two solid lines in this drawing are in the plane of the board. The wedge represents one of the hydrogens coming out of the plane of the board, and the dashed line represents one of the hydrogens going back behind the plane of the board. A simple carbon compound that utilizes sp3 carbons is ethane. From the two-dimensional Lewis diagram, we see that each carbon has four single bonds. Thus, both carbons are sp3 hybridized. Starting with two sp3 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming the CC sigma bond. Next, the 6 hydrogen sigma bonds form, which affords the final 3-dimensional structure for ethane. The 2-dimensional Lewis diagram for ethane implies that all 4 bond angles are 90. However, employing the basic principles of hybridization theory, we see that the bond angles are all nearly 109.5 degrees. Ethane in 3 dimensions has been determined. We can begin to examine some of ethane's interesting physical properties. For example,
Okay, so both carbons are sp3 hybridized. They try to get as far apart from each other as they can. What do we have for bonds here? These are all sigma bonds. So there's 1, 2, 3, 4, 5, 6, 7 sigma bonds here. So next we're going to look at sp2 hybridization.
Right.
After this commercial.
Professional.
I never answer these, by the way.
similar to the first step of sp3 hybridization, one can imagine promoting an electron from 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with 2 of the 2p atomic orbitals creates 3 new degenerate energy hybrid orbitals. The shape of the new sp2 hybrid orbital is best characterized as one.
Notice there's a regular P left over. Again, this is sp2 hybridization. You have 3 hybrid orbitals, 1 from the S, 2 from the P. Regular P left over is the key. Regular P left over.
S and 2 p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes where you can find an electron 90% of the time. The sp2 hybridized carbon now possesses 3 electrons in hybrid orbitals and 1 electron in a non-hybridized 2pz orbital. When we superimpose all 3 sp2 hybrid orbitals with the unhybridized 2pz orbital onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density of the unhybridized p orbital is shrunk to 1/3 of its size for simply viewing. The 3 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the hybrid orbitals attempting to minimize electron reflection. Thus, they are oriented 120 degrees apart. Your instructor will often draw the sp2 hybridized carbon on the blackboard as shown. Again, remember that solid lines are in the plane of the board, wedges are coming out of the plane of the board, and dashed lines are going back behind the plane of the board. Show how the sp2 hybrid building block takes part in bonding It is important to remember that the electron in the unhybridized 2p orbital has access to both lobes. Each of the three sp2 hybrid orbitals contains one electron capable of forming a sigma bond. Thus, the sp2 hybridized carbon is now capable of forming 3 sigma bonds and 1 pi bond.
1 pi bond.
A simple carbon compound that utilizes sp2 carbons is ethylene. From the two-dimensional Lewis diagram, we see that each carbon forms 3 sigma bonds and 1 pi bond. Thus, both carbons are sp2 hybridized. Starting with 2 sp2 hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the CC sigma bond. Next, the 4 carbon hydrogen sigma bonds are formed, which affords the planar sigma bond framework for ethylene.
So right now, 1, 2, 3, 4, 5 sigma
To
bonds.
form the second bond between the carbons, called the pi bond, we can imagine that the 2 adjacent parallel unhybridized 2pz atomic
There's your pi bond. Overlapping regular p orbitals, overlapping unhybridized regular p orbitals. They're parallel to each other, correct? In the same plane. There's your pi bonds. And that's your double bond.
shear, allowing each bond to retain full valency. The two-dimensional Lewis diagram of ethylene allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bond. When the molecule is represented in 3 dimensions, we see that half of the pi bond is above the plane and the other half of the pi bond is below the plane. An understanding of this electron density within a pi bond will become very useful when predicting the reactivity of alkenes. To gain a better understanding of the pi bond, we should recall the actual shape of the unhybridized p orbitals. When we envision the actual shape of these orbitals, overlap between the adjacent p orbitals is possible, which allows for the sharing of these 2 electrons. However, it is very difficult to draw the molecule this way. Thus, you will often see the pi bond represented in its abbreviated form on the right. Understanding the pi bond helps us realize why geometric isomers are so.
How many equivalent orbitals are we going to get this time? 2. Now watch this. If we get 2 equivalent orbitals, that leaves how many unhybridized p's? 2.
Similar to the first step of sp3 and sp2 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with one of the 2p atomic orbitals causes 2 new degenerate energy hybrid orbitals.
2 regular p's left over.
The shape of the new sp hybrid orbital is best characterized as 1 part s and 1 part p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes where you can find the electron 90% of the time. The sp hybridized carbon now
These just look like mushrooms, right? But the higher electron densities here look like mushrooms.
Possesses 2 electrons in hybrid orbitals and 2 electrons in the unhybridized 2p orbitals. When we superimpose both sp hybrid orbitals with the unhybridized 2pz and 2py orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density in unhybridized p orbitals is shrunk to 1/3 of their size for simpler viewing. The 2 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the orbitals attempting to minimize electron repulsions. Thus, they are oriented 180 degrees apart. Before we begin to show how the sp hybrid building block takes part in the it is important to remember that the electrons in the unhybridized 2p orbitals have access to both levels. Your instructor will often draw the sp hybridized carbon on the blackboard as shown. Again, solid lines are in the plane of the board, shaded lobes are coming out of the plane of the board, and dashed lines are going behind the plane of the board. Each of the 2 sp hybrid orbitals contains 1 electron capable of forming a sigma bond. The sp hybridized carbon is now capable of forming 2 sigma bonds and 2 pi bonds. A simple carbon compound that utilizes sp carbons is ethyne or acetylene. From the 2-dimensional Lewis diagram, we see that each carbon forms 2 sigma bonds and 2 pi bonds. Thus, both carbons are sp hybridized. Starting with 2 sp hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the cc sigma bond.
Sigma bond?
Next, the 2 carbon hydrogen sigma bond form, which affords the linear sigma bond framework for ethyne. To form the 2nd and 3rd bonds between the carbons, called the pi bonds, we can imagine that the 2 pairs of adjacent parallel unhybridized 2p atomic orbitals overlap. When they overlap, the 4 electrons can be shared, allowing each carbon to retain full valency.
So for a triple bond, 1 sigma and 2 pi bonds, right? How do you get a pi bond? The overlapping of parallel p orbitals in the same plane.
2-dimensional Lewis diagram for ethyne allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bonds. When a molecule is represented in 3 dimensions, we see that half of each pi bond is above and below a plane. An understanding of this electron density within these 2 pi bonds will become very useful in predicting reactivities of alkynes.
All right. Let's go to our quiz. Let's go to the last page of the quiz. Let's answer the questions. Then we're going to look at some examples of how, and we're going to be done. We are timing out absolutely perfectly, I think. Let's do this right here. We're going to do questions 29 and 30 for the quiz, and then we're going to look at some how examples. Which of the following statements is correct? The overlap between an s orbital and a p orbital is called a pi bond. True or false? S and a p pi bond. No way. How do you get a pi bond? The only way to get a pi bond is overlapping parallel p's in the same plane. So there's no way that's true. The overlap of 2 s orbitals in H2 is called a sigma bond. Good? Yes, that's good. We talked about that. You're going to have 1 electron spinning one way, 1 electron spinning the other way. Hydrogen, hydrogen. When you get out of that, H2. That's good. HF is formed from the overlap of a hydrogen 1s orbital and a fluorine 2s orbital. Oh, this has to be a 2p. So the only good one out of that is number 2. Okay, number 30 looks exactly like the test question. Number 30 seems to look exactly like a test question. How many sigma and pi bonds are in the following molecule? Well, if you have a double bond, you know that one of them is pi and one of them is sigma, right? If you have a single bond, what is it? Sigma. 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 If you have a triple bond, what do you have? One sigma and 2 pi's, right? If you have a triple bond, here, you have pi plus a pi plus a sigma, correct? 1 sigma and 2 pi's make a triple bond. So this is sigma. So what do we got for a total there? It looks like we've got 3 pi's. How many sigmas? 5, 7, huh? 7 sigmas and 3 pi's. 7 sigmas and 3 pi's, yes? Now, let's talk about the hybridization of these. If, let's take this carbon right here. What is the hybridization of that carbon? What is the hybridization of this carbon? It has 2 pi bonds, correct? If it has 2 pi bonds, it's sp. This gives it the 2 sigma bonds, an s and a p, right? Sigma bond is the overlap of s and p here. 2 pi bonds are 2 regular p orbitals left over. You're starting with 4, right? Starting with assume it's s. You should assume it's sp3. But oh no, we've got double bonds. Every time we have a double bond, we got to reduce this. If we have one double bond, like this one, carbon right here, it's sp2 hybridized. It has to have a regular p left over to make the double bond. This carbon here, sp2 hybridized. This carbon here is sp hybridized because you have to have 2 pi bonds. You're going to have 2 p's, 2 left over. What's the hybridization of this carbon? It's the same, right? Because you've got a sigma, sigma. So the hybridization will match up sigma bonds. The hybridization matches up your sigma bonds because that leaves you the leftover pi bonds. Okay, we added to this. We pretty much added the answer to the test question, I believe. I think so. Okay, now let's just look in our learning guide to finish up what all looks like. Again, we're timing off perfectly. I've got a lot of stuff in here. It's like a new textbook. The video covered a lot. You can look at some of these structures. We didn't look at the hybrid orbitals. We only covered sp. But if you get to question or page 22 on this, you've got an out question that looks like this. And you get to manipulate this in out. if you have PCl3, which is in this structure, and you see a picture like this in all, you're gonna have a non-bonded pair up there. Or you can just draw it out. If you have PCl3, and if you draw the structure out, you got a 3-1 out of that. Then, how many are bonded? How many atoms are bonded to the central atom? 3 in the green, right? 3. If you consider only the 3 outer atoms, what shape do they define? Triangle. Consider the bond angles should be on the central atom. Do they all have approximately the same numerical value? Yes, they're going to be about 107.5 degrees. Or what approximate value? The only choice you can get close to the 107.5 is 109. Again, the word approximate. Now, does the central atom lie in the same plane divided by the 3 other atoms? No. What would be an example of when they're in the same plane? Would just be like a boron trifluoride, where it's 2-dimensional. But when you have a 3-dimensional, when you have a structure like this, the same plane of the central atoms, if you took this central atom and just sliced it, right? And the terminal atoms would have to be on this in the same plane. You can do that with trigonoplanar if I take this thing apart. If I do this, in the same plane, then the terminal outside atoms would be in the same plane. Are all 3 positions above the central atom equivalent, or is one of them different? They're all the same. And a 3-1 would get us trigonal pyramidal, right? Trigonal pyramidal for a 3-1. Another odd question. On the next page. So what you could do for the unbonded pairs, you need to actually draw the structure out. In this example, it's ICl5. Rotate the molecule. How many chlorine atoms are bonded to the central iodine? 5. A molecule with square pyramidal geometry will result if one of the outer atoms will remove from an octahedral molecule. Doesn't matter which of the outer atoms is removed. Does not. Are all the outer atoms geometrically equivalent in a square pyramidal, or are there 2 types? There are 2 types. What approximate angle do you get for the chlorine atom? Got 90s. You're going to see in the diagram. And opposite from it, you're going to end up with some 180. All drop downs. Name of the geometry, square pyramidal. So these are all drop downs. Not bad. Shouldn't take you too long. Now, what we just covered, hybrid orbitals and sigma bonds. So a sigma bond arises from the straight on overlap of two atomic orbitals. The electron density lies along the axis of the two bonded nuclei. Okay, so again, we could have an electron spinning up here and an electron spinning down here. And this is CH4 here. Got hydrogen electron. And you've got an electron here, hybridized. This structure, you're going to have to do Google images or draw it out, CH2O. You actually end up with a structure like this because oxygen has two bonds. Now, what do we have here? Got a sigma and a pi, right? We get a double bond. We have one of those got to be a pi. Sigma, sigma. How many sigma bonds do we have? 3. That means that is sp2. If I add up the 3 sigma bonds, I get sp2. That would leave a regular p orbital for the pi bond, right? Regular p orbital for the pi bond. So sp2, and this is actually a 3, 0, which would give us 1. In this one, we would draw this out. We've got carbon, carbon, carbon. Got 1 hydrogen. No hydrogen in the middle. So that means in order for this this first and second carbon to have 4 bonds, that would be our structure. This is our CH, this is our C, and then our CH3. Now, let's see, carbon 1 and carbon 2. So they're calling this carbon 1. I'm assuming carbon 2 and carbon 3. Let's see what we got here. What atomic or hybrid orbitals make up the pi bond? Well, there's 2 pi bonds on that thing. So one of these is sigma, one's pi, but it's going to be the overlap of 2 p orbitals, correct? A regular p orbitals. And the overlap of 2 p orbitals on both carbons. One of the pi bonds would overlap there, but there's 2 of them. How many sigma bonds does carbon 1 have? Switch colors. This is a sigma. And what is a triple bond? A sigma and 2 pi's, right? A sigma and 2 pi's. So one of these is sigma. So carbon 1 has 2 sigma bonds. How many pi bonds does it have? It? These 2 right here have to be pi bonds, right? Triple bond, a sigma and 2 pi, so it has 2 pi. What does that do? That ends us. Got a couple of minutes. Let's do the quiz question on the bond triangle, huh? Let's do the quiz question on the bond triangle. Let's see what it looks like. Number 21, based on the bond triangle on the quiz, which of these, based on the bond triangle, which of these covalent compounds has the greatest ionic character? To get the greatest ionic character, which is in the top of the triangle. You want to get to the top, the greatest ionic character in the top of the triangle. Some of them are on here. I'm pretty sure you can kind of search, or you can probably do, if you do the electronegativity difference, you can come across on the y-axis, you might find them. I think they're on there. I don't think the top. You want to get to the top of the triangle. Which one of these in 22 has the greatest covalent character? Which one of these is closest to the bottom right of the triangle? Closest to the bottom right would be your greatest covalent character. Otherwise, the top is going to be the greatest ionic character. Again, this triangle does another dimension to it. It's not just difference in electronegativity. It takes into account the average. I think that's it. So I'm very happy where we're at. We turned out here perfectly. I think we got through everything we needed to get through. I think you can do all of the owl. I think you can finish up the quiz. I think the quiz is due what, Sunday night, but I will do Monday night. Yeah, the quiz is due Sunday night. All right, good deal. I emailed you out the what's on the test. Again, I would do. And that should do it.